Today we're going to go over acid-base theory, specifically the Bronsted-Lowry model. The Bronsted-Lowry model looks at the movement of protons during an acid-base reaction. In other words, where is the hydrogen going? In this model, we view acids as proton donors and bases as proton acceptors. Here's an example of an acid-base reaction. Here we have hydrochloric acid and sodium hydroxide reacting to give us sodium chloride and water. The acidic hydrogen in the hydrochloric acid is attracted to the partially negative charge on the oxygen in the sodium hydroxide. This is important because it means that during the reaction, the bonds don't break and then form, but break and form at the same time. Lastly, every acid and base has what's called a conjugate. A conjugate is just an acid or base that has already donated or accepted a proton. In the reaction we have here, NaCl is the conjugate base, and water is the conjugate acid. This is because if you look at your reactant side, you can see that HCl gives over its hydrogen to the NaOH, which then means that NaCl is the conjugate base, because it's already donated its hydrogen. And then sodium hydroxide ends up accepting that hydrogen, so then the water that's the product ends up being the conjugate acid. Let's do another example. Here we have ammonia and methanol reacting to give us ammonium and methoxide. Take a moment and pause the video and see if you can figure out and label the conjugate acid, the conjugate base, as well as the acidic hydrogen. Alright, so if we look at our reaction, we can see that NH3 ends up gaining a proton on our product side. So based on the definition of our conjugate, we would go and say that NH3 is the proton acceptor. So then NH3 must be the conjugate acid, and then methoxide, CH3O, must be the conjugate base, because the methanol gives over its hydrogen to the ammonia for our reaction.